you so much, Tess. I'm very happy to be here. This is a class that we will teach jointly with Giulio, who's here, Giulio Biroli. And so I want to talk about that thing, the random landscapes, so but of data science. So, of course, the way we got to study this thing came from statistical physics initially. That's the place where you naturally have very high dimensional random functions, which are what the random landscape will be. And you will see, I will today touch a little bit on physics, on spin glasses, but that's not the goal of these lectures. These lectures are to bring you to these questions of artificial intelligence and machine learning, high-dimensional data science. So let's start with, so first, maybe I should start with this story that my friends know. So, you know, at some point at NYU, a long time ago now, at Courant, I was the director, we were starting a center for data science a long time ago, something like 15 years ago. And the future director was somebody everybody knows today. That was Yann LeCun, who then, of course, went to Meta and got the Turing Prize and this kind of thing. But then at some point, we chatted just about mathematically scientifically what we were doing. Yann is French, so we were both having a glass of wine. Everything was cool. And he told me what he was doing, and then I told him, and then at some point we both thought, and of course up to then I had no clue what a neural net was or what machine learning wanted to do. 15 years ago it was much less in the newspapers than today. And then we just both had the impression that these two things were the same thing, related, right? And this story of today will be essentially, so initially we wrote a paper with Jan and Anna Choromonska, and that kind of said there must be a link, which was kind of essentially a numerical paper. And sometime later, I found a link between this kind of random landscapes of physics and random landscapes of data science with one very specific example, which is Tensor PCA, and I will try to get there. And once we understood this link, things where the language was obvious. So let's go for that. So first, of course, I will talk neither about statistics nor about physics, but about math. So, and to understand what are the natural questions about random landscape. So what is a random landscape? For me, it's just simply a real valued function, smooth, of n variable. So of course, let's say on a manifold, if you want, on a compact manifold, think it could be on Rn, think Rn, the sphere, whatever, in n variable, and n will be very large. That's the important thing. So we want a function random of very many variables. Right? That's the mathematical object. Smooth. It could be not smooth, but that's not the problem here. Okay, so take a function as smooth as you want of a billion variable, and it's 10 to the 9, and with real valued and random. And now you're interested in the basic question of optimization, which is how do you find the minimum of this thing? How hard can it be? Or maximum, right? Or maybe not the minimum, maybe a value very close to the minimal value. Okay, so that's the question. So I'm just asking an obvious question, optimization for smooth function, but in very high dimension. So, as I said, if maybe you don't want to, you cannot find the minimum, maybe you can reach some low values, right? So, of course, optimization has been a theory in math and in engineering for centuries. So there's a huge theory. But the twist here is that the number of variables will be very large. Most of the things you learn about optimization in a class of optimization are done for low dimensions. Okay? So in particular, even if somebody tells you this algorithm, the Markov chain converges exponentially fast. Cool, then the problem is finished. Except no, because if the constant in your exponential depends on n very badly, then maybe this convergence is super slow. Okay, so these type of questions are another layer on optimization. Okay. Right. So I isolate here two questions about that. In fact, normally I take three, but here the physics part I will take out essentially, because you already know physics, right? So the first question here is topological, right? If you have a function in very high dimension, what is the topology of this thing, right? Of course, every time you think of a function, you think of a function of one variable. That's a function, right? So you think of the graph of a function, but that's in 1D. What if you're in dimension a billion, right? So what is the topology? So for instance, think of the level lines, right? You cut your graph at a certain level and you look at the set where the function is below that. Can you understand the topology of this in high dimension? How is it? And, or, you know, what are the number of critical points? Or what are the number of local minima, of local maxima, of saddle points of index, whatever, okay? So this is a topological question. This is a question about the shape of your function, all right? But so how do you measure topological complexity? I'm saying you can say a function is complex or not complex topologically. How do you measure that, right? This seems to be more complex than that, right? But how do you measure that? So that's the first question. Then the second question is, once, you know, if you have this random function and you have an idea of what complex means, topologically complex means, the next question is it complex almost surely once you fix such a realization, or in some average sense, right? And that could be different. In physics, of course, it's annealed versus quenched, and we all know that annealed is much simpler. So is it, you know, you may have a function of very many variables, and there are constraints on the complexity of the function which are given by mathematics, by algebraic topology, which is Morse theory, right? There are constraints. But is the function that you've chosen much more complex than what geometry imposes, or not? Is it much less complex than the worst case possible, right? Okay, so that's because maybe it's complex because of the underlying geometry of the space on which you are, or not. We'll see. So these are kind of completely topological questions. For the moment, no physics, no dynamics. Of course, if you want a little bit of physics, if you have a function, think of it for a moment as a Hamiltonian, an energy. Then, of course, the way physicists would look at this would not be the question of finding the minimum, the ground state in physics, is not the natural question. The first natural question would be, what is the behavior of a Gibbs measure at low temperature? Right? So you know what a Gibbs measure is, I guess. Am I wrong? No. Then the question is, okay, this function is complex. How is this seen in the behavior of the Gibbs measure? Again, for a machine learner, a statistician, a data scientist, this question is totally useless. Okay? They don't give a damn about the Gibbs measure. But we do. So then once you have this question of the shape of this function, the next question is, how do you understand the complexity, the difficulty to go down, to dynamically explore this, to find low values, to go to the bottom of this complicated landscape? So this is the landscape. The function is like the altitude. And the question is, you want to go down, do you want to go deep? How hard is that, right? So of course you have a gazillion of, as I said, optimization is an enormous field, and engineering using that is gigantic, in particular today, given how, what the stakes are. But we'll explore the simplest thing, which are in fact used basically. So the natural thing for optimization is gradient descent, right? How do you go down? You take the gradient, your function is smooth, remember? You take the gradient, you follow negative gradient. In the end, you should go down, right? You could have gradient flow, gradient descent. You could have stochastic gradient descent, or if you like physics more, you could add a bit of more noise and have Langevin type dynamics, okay? All right, so these are the natural algorithm. We'll have to talk about them. And once you fix such an algorithm, so you have fixed a function, you have a sample of this landscape, And now you ask, how hard is it to get to low value and possibly find the minimum using those very simple algorithms? Okay? Not specific things to your problem, just let's say SGD, which is the standard in the industry, stochastic gradient descent. How much time does it take? How much steps does it take before you get to some decent approximation of the minimum? So here are a few questions. How fast or how slow are these dynamics? Of course, if you're a physicist, you're interested more, or a mathematician, in the slow part, because that's the fun part, to prove that things don't work. If you're a theoretical computer scientist, you're also interested in saying that things don't work. If you're an engineer, you're interested by saying that things work. So what are the relevant timescales? How many steps do you have to do? Is this topological complexity I just mentioned, is that relevant? Does it play a role in the optimization algorithm or not? Right? So there, from the start, let me dispel something that even professional optimization people keep, a mistake that they keep making. If you say that to anybody who thought 2 minutes about optimizing, you think, of course, no, because of course, yes, the complexity is important, because if my function is this, then if I start here, I will get stuck there, and that's it. Right? It will take a very long time to get out of there. Even if you have noise, it will take very much time. So the question every time you read something on that is, yes, but there are the local minima, let's say. And that's terrible. But maybe not. In fact, I will show you that mostly this is not the important question. Okay? How can it be? We are in very high dimension. So maybe you have plenty of those terrible local minima, but maybe God is on your side and you won't see them. Right? Maybe you don't have that many of them. Entropically. Maybe the entropy of this thing is not large enough so that you don't fall in them. Or maybe you do. Okay, so that's another type of question. Okay, so is topological complexity?
How likely is the answer to this question dependent on the way you represent your function?
No, it's not dependent at all on that. It's very much dependent on where you start your algorithm, and more importantly, how strong the signal is, as we will say when we do statistical physics. When we do, machine learning type things. Okay? All right. Of course, if you do you look at the classical statistical physics problem, it's a spin glass, and you start at random. Of course, before you get to the absolute bottom, you will visit those guys. But you are there in timescales which are not of no interest for engineers. Right? You're in much longer timescales. And by then, the universe has frozen and your company is ruined anyway. So what is the role of entropy initialization? This is exactly, and for what time scale? This is what we're talking about here. Okay. So these are the type of questions. First, questions on the shape, on the topology, then questions on the dynamics. Then we have two types of questions. So what kind of landscapes are we interested in? So there are two, as I just mentioned, two classes of random landscapes here. One is statistical of disordered media. I just mentioned glasses, spin glasses, things of that nature, which means the function you're looking at is your Hamiltonian, and you assume that it's random. Okay, so you have a quenched disorder. The disorder is frozen in your function, and then you want to understand maybe the Gibbs measure, and then maybe the Langevin dynamics for that if you're doing physics. All right. And the other is, so here the disorder is frozen in. It's part of the modeling. Right? Your Hamiltonian is random. For instance, you have random couplings between different sites of spins or whatever. And the other one is high-dimensional statistics or data science, machine learning. There, the function is different. We'll come back to that. That's essentially the innovation of machine learning. We have gone from a standard where, when you study statistics 50 years ago or 20 years ago, of course, everybody wants to be in very low dimension, very few parameters, because high parameters you can do nothing. But of course, machine learning is the contrary. The idea of machine learning is you develop models when you have a network. It may have 10 to the 8, 10 to the 9 parameters. If you think a minute about it, this is crazy. Why do we want to optimize? Why do we force ourselves on this pain, which is to optimize a function of 10 to the 9 variables? Right? In statistics, you choose your model. Why do you do that? Right? So it must be good. Otherwise, they wouldn't do it. So, and so how is this function random? It's random because of the data. Right? You typically have an empirical process. You have a bunch of data, which is random. Let's say IID from an unknown distribution. And this gives a random aspect to your function. You have an abstract loss function, let's say, which is theoretical. And then you have an empirical one, which you have from your data. And this, of course, is random. Okay? And again, you have one sample. And you don't say, well, let's draw again a huge sample. You just have it, and you just work with it. Okay? So in both cases, these are the two things. So in physics, it would be energy. In statistics, it would be loss or likelihood, depending on how you, whatever. And these are the things you want to optimize. So, as I just said, in the first case, the function I call f here is the random Hamiltonian of a statistical physics model with quench disorder. And of course, what is done usually in physics is, of course, that you look at the Gibbs measure, as I just mentioned before. So here you put your function f here, the Hamiltonian, the inverse temperature, you normalize, of course, and then you have some a priori measure mu0. And of course, statistical physics consists in studying the behavior of this thing at different values of beta. So, and of course, in physics, typically, of course, in this type of model, of course, it's simpler when beta is close to 0. When beta is 0, your measure is just the initial measure mu0, which is supposed to be simple, like a uniform measure. So this is, and it becomes harder when beta becomes large, which means when the temperature goes down, right? The approach I'm advocating here is when you start with the topology, you start, in fact, with what's happening at temperature 0, right? You want to understand what's going on for the function f itself, and then maybe understand. So you would do what the contrary of what is always done in statistical physics. You would start from temperature 0 and try to raise the temperature, right? If you could manage to get the complexity. So this is what. So we could look here a few examples I have in mind. I will not read all of them. One of them would be spherical spin glasses, and I will just talk about this. And there are other. If I had more time, I would talk about random interfaces and whatever. But since I want to stay on track to go to statistics, I will just give you one example of physics, okay? Which is the first one, spherical spin glasses. In these questions, let me already, since I will be, of course, pushing the math aspect of these things. In this question, there is a tool which is hidden all the time. A priori, it has nothing to do with this, but in fact, the tool here is random matrix theory. So where is random matrix? If I give you a random function of many variables, why would you have a random matrix? Why would it play a role? Okay? And so the answer is, the random matrix theory, RMT, lurks in the behavior of the, if you take a function, you look at its Hessian at a point, it's of course a real symmetric matrix. If your function is a function of a very large number of variables, this is a very large random, and if the function is random, this is a random matrix. If it's a function of many variables, it's a random matrix in high dimension, which is of course what random matrix theory is about, right? So here, the random matrix, which is important, is the Hessian of the function at critical points. Okay? Not everywhere a priori, but for the study of the topology, what's important is this. You look at all the critical points. Let's assume for a moment that your function is non-degenerate and that you are on a compact manifold. Then you have a finite number of critical points. It may be large, but you have a finite number of them, right? Then you look at the collection of all those Hessians. It's a collection of random matrices, and it contains all the information you need about this complexity, okay, as we'll see. So the other source of random landscapes, as I just said, is, of course, statistics, machine learning, data science, artificial intelligence, whatever. And the random function has this shape. You have a loss function. So this is, so you have first you have a task. When you do machine learning, you have two things that are given to you, which is a task and data, and a data set. This is given. So the task is, for instance, here, learning. Of course, in machine learning now we say learning, which is a word which normally means simply estimating. Right? In statistics, it's just estimating. It's the same word. It says the same thing. So you have a parameter. Let's say here I call it theta, which is in Rn, and this theta is unknown, and you want to learn it. You want to estimate it. Right? So you have a bunch of IID random variable, yi, you have capital M of them, drawn from a distribution which is unknown to you, but which depends on theta. Okay? And then, if you're a good statistician, machine learner, AI guy, you devise a function L. That's your choice. That's the next step. So you have the data and the task. That's what's imposed on you. Then as a statistician, you choose L, right? You choose the loss function. Of course, then you have thousands of pages of statistics to tell you how to do that or not do that, or to estimate how efficient it will be. And then what you typically want to do is to take the how do you choose L? You choose L such that the expectation under your unknown probability distribution of L, of y and theta, should be minimized. You don't have access to this population loss, as they call it, to this expectation, because you don't know the unknown distribution, but you have access to this empirical version. So then maybe you can take this empirical thing and try to find its minimum and hope, cross your fingers, hope two things, that it's not too hard to find the minimum, and second, that the minimum has something to do with the truth, right? With the true value of theta that you don't know. Okay, so here this function depends on many dimensions, we should remember.
I'm sorry, but it's not very clear to me how this formulation of equation 1 connects to the things one usually says in machine learning, where you take linear function composed with non-linear, linear.
This will come. It's in L. Your statistical structure is hidden in L. The loss function. The whole thing you do when you build a network is you build an L.
And what is Y?
Y is the data. Okay, so I give you, for instance, 1 million pictures, and let's say I do supervised learning, and I tag with them, let's say, a picture. Yes, there is a cat in the picture. No, there is no cat in the picture. This is my data. Big pictures, and yes or no. Then you're free to choose the L you want. In machine learning, you have good ways to choose L. You put the L there, but then the next step is, so that's the statistical part, choosing the right L. Then you have the optimization part, finding a minimum of that, which might be, and of course before that, so in the statistical step, you want to choose this L in such a way that the minimum of this would be related to what you want to find, of course, and it's not clear. All right, so here are important things to remember. The parameters, M is the size of the data. For me, N here will be the dimension of the parameter you want to estimate, which is usually, again, since this parameter could be very high dimensional, and D was the dimension of the data. Okay? And they are not the same. All right.
I thought you said M was the dimension.
No, M is the number of data points. D is the dimension of the data. So if you have a picture, D is the number of pixels. M is the number of pictures. All right, so Y is the data, random variable in RD, and from which you try to estimate the theta. L is given by the statistical procedure. So, for instance, if you're a statistician who has not yet learned anything about machine learning, you do the basic statistical procedure is to take maximum likelihood. So you compute the likelihood. Typically, you take a log, and maybe you take a negative, because here I want to find minima instead of maxima, and that gives you your L. If you're smarter, you could have include the machine learning network if you do use one. Okay, so that was the question that was asked over there. So we have three integers, n, m, d. N is the dimension of the parameter, m the size of the number of data points, and d the dimension of the data. And there will be various regimes depending on all this. What is the classical regime? The regime which goes back to Laplace or Gauss or whatever, Bayes. It's of course a situation where this m is gigantic, is enormous compared to n and d. Okay, so when you have a very large number of data, of course this is what we learn in class 101 of probability and statistics, the law of large numbers, central limit theorem, so when m goes to infinity. So if all these numbers are large here, it means there should be a regime where when m is very large, things are simple, right? But in practice, when your n is itself 10 to the 9, maybe the m you need is 10 to the 10 to the 9, right? And then too bad, you don't have that much data. Okay, so why are those random functions important? So let me state again what we do in this statistic thing. I re-say what I just said here. So you have an unknown probability distribution. Let's say on an open U of RD. That was the capital D, but now it's a small d. Then you have a loss function, which is defined as V cross U. V is in the space of parameter. And then, oops, the goal is usually to find the minimum of what I said, the population loss, which I call phi here. This population loss is usually unknown because you don't know the distribution. So you don't know this population loss, but what you do is you do this, as I just explained, you have data, and you compute this empirical loss, which is supposedly some approximation to the population loss. And again, it is one when m is sufficiently large, but in practice, m will not be sufficiently large. Okay. So the natural regime, the classical regime that I just mentioned, is when d and p, the dimension of the data, the dimension of the parameter are fixed, and the size of the data sample goes to infinity. Then it's easy to do. I mean, you can optimize. It's a simple function. You know what to do. So for instance, you could do that. You can do gradient descent. Gradient descent is just this. At time step L minus 1, you are at a certain position. The next position is this minus delta times the gradient of your empirical thing taken at the point before. That's gradient descent. Here you have a choice of this time step. You have the choice of two things, in fact. You have the choice of the initialization, which is crucial, where you start, and the size of the time step, and then, of course, the number of steps you do. So in this classical regime, it's well known. I won't bug you with the technical assumptions, but it's clear, it's well known that this empirical loss here will be, in the right regime, will be close to the population loss for this gradient descent to find the minimum. This thing, in fact, there are natural theorems which explain that the limit of GD, of course, will be gradient flow. And then you have the question, does gradient flow go to the minimum? Of course, again, gradient flow, depending on where you start, could not go to the minimum. Again, if you start there and you do gradient flow, you end up here, right? So this is understood. You could, if you prefer, if you want to do something more physics-y, you could add some noise to that to have a discretization of Langevin rather than a discretization of gradient flow. Okay? So now let me introduce stochastic gradient descent. If you don't know what that is, it's a variant of this thing, which is what is used. Nobody uses gradient descent in optimization for these big tasks. So there are plenty of variants of SGD, and I will give you just one. So you could have different sizes of batches, different learning rate, reuse or not. So let me just define the simplest thing. The simplest thing is this, and look at the difference. Here you have XL, which is at the position of your algorithm at time L. It's the position at time L minus 1 minus a time step as before, time the gradient of L as before, but before we took the average of the gradient on your whole data set, right? Whereas here we just take it on one point. That's called online SGD. So it's the simplest version. So you have one data point that comes, you take the gradient of L and the place where you are using this data point, and you move by this step of size delta. All right? You could do something more complicated. Instead of taking just the last point, the last data point, you could take a batch of them, the last 75 data points, right? And do the average of these, and do that to use your step. If you use at every step the whole sample as a batch, so that's full batch instead of small batch, then in fact you're doing the empirical gradient descent I was explaining before. Right? The thing I was giving you before, you were taking the whole thing at every step. What's the interest a priori of doing this? So of course, much less heavy, because at every step, you just take one data point, put it there, do a move. Right? Instead of recomputing, if your things are huge, instead of recomputing the whole thing. Okay? So this is a very simple algorithm a priori. And so, of course, you have to add how you start. So let me call mu the random initialization. You don't want, of course, to study, you could, and some people do, but you don't want to study an initialization which is informed, where you already are close to the truth. Right? That's not what you want. You want to start with something with no information, random, and hope that you find the true minimum. Okay?
So the gradients are exact here.
Yeah.
Yeah,
you can see, you know, there are a gazillion variants possible. I also ask here you could do, for instance, here I'm saying you could do reuse, right? That is, you could use all your data and use them again. And you, as I said, you could make different. We'll see that it's important. Different learning rates here, different size of batches. You could different approximation of the grade. For the moment, you assume that you have your loss function. And in this case, it's true that the loss function is very simple. So
you can pen and paper.
Pen and paper, not bit difficult. So you can. Okay. So what is the problem at hand here is to understand the evolution of this dynamics in the regime when both the dimension of the parameter, the dimension of the data tend to infinity, but when m, the size of the sample, is not too large. You're not in the classical regime where you have a gigantic number of data points. Okay? Which is, of course, the limitation in those things. When people think big data, they think, no, we have as much as data as we want. That's exactly the contrary. We have big data, but not many data. Right? The data may be large, each of them, and be a complicated picture, but you don't have enough given the hardness of the fact that you have to estimate 10 to the 9 parameters. Maybe you need too many pictures that you don't have. And why is right now, you know, you have all these trainings for ChatGPT, whatever, that, you know, is making the planet boil because of this. You need an enormous amount of data. So here we don't want that. So where is random matrix theory hidden now? Let's go back down to her. Where is random matrix theory hidden in this question? I say that so that if you don't want to look at the proofs, if you just remember this sentence, that's essentially most of the proofs. Okay, so random matrix theory here lurks in the behavior of the Hessian of the function, the loss, or the Gramian, I say what that is, along the optimization trajectory. So for the statics, it was at critical points. Here it will be along the trajectory. We'll see how that is important. Okay, so that is GD. So these are the two questions, right? I've asked you the two questions. You take a random function of very many variables, Hamiltonian of physics, loss function of statistics, and then you start at random. So first you study the topological complexity of it, and then possibly the Gibbs measure if you're a physicist, and then you want to understand the power of these optimization dynamics. And of course, here you could say, no, I want to study Langevin instead of SGD or whatever. These are just variants, as we'll see. Okay. So these are the two questions. Now let's go back to the first question. So I give you a reminder here of it's a very short class on topology, and that's called Morse theory. So consider a smooth real value function on the an n-dimensional compact manifold. If you don't know what a compact manifold is, think the sphere. Okay? Then how can you understand the topology of defined by this function? So one way, as I said, was to look at the sub-level sets. You look at the set of points, A of u, the set of points where the value is below u. Okay? And of course, you will be interested in low values for you here. So now you can ask, this gives me a set, you can ask what's the topology of this set, right? So think of something like this. If you cut, you will see that your set will be a bunch of intervals, right? So you could ask yourself, how can I describe this? So if you know what the earlier characteristic, you can look at the earlier characteristic of these level sets. If you don't, I will see other things. You could do something completely different. So this is a purely topological thing. You could look at something different, which is more related to what we do for. You understand that this topology is probably related to the performance of dynamics. But now let's look at something else. We look at the number of critical points. So I will call crit f n k the number of critical points of f on the manifold, which are of index k. So remember what the index is. If you take a point, you look at its Hessian, its second derivative. It's, as I said, a real symmetric matrix. You can look at its eigenvalues. Let's assume that the critical point is non-degenerate, so you don't have a zero eigenvalue. Then you have positive and negative eigenvalues. The index is the number of negative eigenvalues, right? So index 0 means no negative eigenvalues, which means a local minimum. Okay? Index 0 is local minimum. Okay. Index n, if n is the dimension, is local maximum. All right, so here you can fix the number, the index, k, and b here I would say look at the number of critical points, which is values in the certain subsets, for instance, below a certain level. Right, so you take your function and you count how many, let's say, how many local minima do I have below this level? Right, here I have 1. If I put the level here, I have 3. Okay? Now, these two questions are related, and that's what's called Morse theory. This goes back almost 100 years now. There's Morse inequalities give constraint. I won't spend time on that, but between these two things, the topological invariance and the number of critical points, under the assumption that the function is Morse, which means that the Hessian is non-degenerate, as I said. You can imagine that if you take a random function, it can very easily be generic, that is Morse, right? It will not hit these particular things. So let me say so for instance, the simplest, the weakest Morse inequalities say that the number of critical points of index k is larger than this Betti number of the manifold. The strong Morse inequality gives you something like this, which relates this number of critical points and the Betti numbers. And even more, that the alternating sum of critical point, of number of critical points, depending on the index, is equal to the earlier characteristic of the manifold. Okay, I could do that with more complicated stories, but that's the minimum type of thing. So in particular, this tells you, let's see at what is this type of crazy things, say in the case of the sphere, the simplest possible compact manifold maybe. Right, if you take the sphere, then in fact, those Betti numbers are, I think I explained that in the next slide. Yeah, so if you take the sphere, the Betti numbers are all zeros. The sphere is in dimension n minus 1, right? So you have Betti numbers from B0 to Bn minus 1. They are all zeros except the two extreme ones, which are 1. So the weak Morse inequality that I just told you here are just stupid. They say the number of critical points is larger or equal to 0, right? When k is between 1 and n minus 2. And the crit 0 is at least 1, and crit n minus 1 is at least 1, which means simply that there is a minimum and a maximum. So the weak Morse inequality tell you nothing. Just there is a minimum and a maximum. The strong Morse inequality gives you something much more interesting. It says this number here, this alternating number of number of critical point is 0 or 2. Right? So you have this kind of interesting balance. So now, okay, so you see there's a big difference between the two, but so now the question, if I take a typical function, let's say a random function of some form, is it more complex than the simplest bound given by Morse? Morse tells us on the sphere, the sphere is so simple topologically that just saying you have a minimum and a maximum, and otherwise this constraint here. So if you take a random function, is it more complex than that, or is it complex or not complex? So let's take a very simple, so what I'm saying here, that it can happen that smooth functions of very simple manifolds, like the sphere, have exponentially complex landscape. So by exponentially complex, I mean the Betti numbers or the number of critical points are exponentially large, right? So imagine you want to optimize a function that has 10 to the 10 to the 9 local minima, it may be difficult, right? Or maybe not.
So you understand complexity in the sense that the function can have a lot of local minima?
This one, the topological complexity. Then we have other ways to define. But yeah, for the moment I'm talking about this topological complexity.
Quantitative measure is a number of...
It could be that, or by Morse theory, it could be the topology of the level sets. Right, the Betti numbers that characterize the topology. If you know what the Betti numbers are.
So if I have a lot of Betti numbers and I feel that my function is complex?
By the Morse inequality, yes. Okay. That's, let's see. So let's take the simplest function. What kind of simple function can you take on a sphere? Right? So one of them is just the latitude. If I draw the sphere like this, you take, and I call this axis x1, it could be x1. That's not very complicated. That's the latitude. That doesn't seem like a very complicated function, right? It has obviously a minimum at the south pole and a maximum at the north pole, right? Nothing really fancy. So maybe that's a polynomial of degree 1. So all right, maybe you can go to degree 2 or degree 3. Okay, so let's take a polynomial of degree p. Okay, and to make it simple, let me take a homogeneous polynomial of degree p, which is a perfectly natural set of functions on the sphere. Okay, so I take the simplest. Of course, this is purely mathematical and no interest for nothing, right? But let's take that. Let's take a homogeneous polynomial of degree p. How complex can it be? So here, when the dimension, I want to insist on the fact that now this function is trivial. P is fixed, 3, but the dimension, the number variable is large. Is that a complex or not complex function?
No, this may be a silly question, but what's a polynomial of degree p on a sphere? Does this depend on how you parameterize
It's define it on the on the space. It's just some. I will write it, but it's just. That's this.
But this is defined on the eigenfunctions of the sphere in some sense.
What?
This is defined on nice functions of the sphere in some sense.
No, this is defined on Rn if you want. But in particular, you restrict it on the sphere. So what I mean here, you take a polynomial and you look at it on the sphere. Okay? This is what we're doing here. I'm putting this on the sphere just to simplify things. I could put it on Rn, a little more complicated. If I put it on the cube, then it would, all hell would break loose. Then it's much more complicated. Okay, so how complicated can this function be? Right? So clearly it's not very complex when p is 1, as I mentioned, right? It's the latitude. Polynomial of degree 1. Polynomial of degree 2 is not very complex either. Right? Because of course if you have polynomial of degree 2, essentially you can reduce it to sums of squares. You would have critical points, but not many. Right? How many critical points do you have to a quadratic form on the sphere? Okay, I let you think of that. That's not very hard. Anyway, it's not exponential. But as soon as you take p equal to 3 or larger, all hell breaks loose. Right? You take a cubic, then terrible. Of course, not necessarily. If I take this cubic, x1 to the cube, that's not a very complicated function, right? You have a minimum, a maximum, in fact, a minimum, maximum, and critical points at the equator, but it's not very complicated. So that's what I'm saying. Cubics can be terrible. But here's a nice theorem. The maximal number of critical points for a homogeneous polynomial of degree p is this. That's a theorem, which tells you that, in fact, it's growing. The number of critical points is growing exponentially. Right? Take p to be 3. This tells you that this number is of the order 2 times 3 to the power n minus 1. Right? So the number of critical points for polynomial of degree 3, the worst possible is this exponential number. All right? So a stupid polynomial can be a horrible function. Can you imagine a polynomial like that with exponentially many holes? But that's how you should think. So there exists such a worst-case polynomial. This is due to Korzhashov in 7 years ago. So the worst possible polynomials of degree p are exponentially complex. And the complexity, the log of this number is essentially of order log of p minus 1. When you take the log of that, divide by n, you get log of p minus 1. So the answer to that, so I'm telling you, take the stupidest manifold, the sphere, in high dimension, take the simplest possible function, a polynomial, it's already impossible to minimize. Right? It's already horrible. So, of course, you could say, yeah, but this is a worst case. This is a kind of strange frame of mind of theoretical computer scientists and algebraic geometers who invented this thing. Right? Nature is not like that. You agree, right? No. Nature is like that. So this is a worst case scenario. Now let's be reasonable. Pick your polynomial, this polynomial randomly, generic. So you take a random polynomial like that. So you take these guys to be random. Right? So you take them, let's say Gaussian, IID, and 0, 1. So you take a random polynomial now. This one, for instance, is not the random polynomial in this class. It's just a very specific polynomial. So take a random polynomial. You will not have this worst case thing. Now, will that be complicated or not? So here is one. So here, okay, maybe here I made, forget this. Here it's a polynomial. I added all these homogeneous terms, but you can take only one and it will already be interesting. You say that you take the coefficients here to be random, let's say IID Gaussian. So this function here is obviously centered if my Gaussians, my A's are centered. It's obviously Gaussian if my A's are Gaussian. And the covariance, if you compute the covariance of that, is very simple. You see, again, forget this term. I'm really sorry. I'm just taking one of these terms. If you compute the covariance of that, it's very simple. You take the sum of AX times sum of AX prime. What you get is easy to compute, and you get this thing. You get a constant times the inner product, the covariance between the point X and point Y is the inner product to the power P. Very simple, trivial computation. Which means that this is also a function of the distance, right? Because remember, we're on the sphere. So if I give you the inner product, I'm giving you the angle. So I'm also giving you the distance. So this, you could look at it now like a probabilist. Instead of saying I'm an algebraist, I'm looking at a random polynomial. I have a random function on the sphere, and it's a Gaussian random function. So the only thing I have to compute is covariance structure, and then I know the Gaussian distribution. So it's centered, and the Gaussian distribution, the covariance is isotropic, and it has this shape. Okay? So in physics, this thing is just called the overlap. And the interesting part is that so this is an isotropic Gaussian function on the sphere. These isotropic Gaussian processes, or their covariances, what are the functions which can be the covariance of a Gaussian process, which are positive definite? This has been classified in Vienna almost 100 years ago by Bochner, Schoenberg, the students of Bochner. And in particular, so this is entirely understood, and the class of such thing is exactly this. So the example I just gave you is the most general example of an isotropic. So you could enter this field by two ways. One, you are a probabilist and you want to understand the Gaussian process with isotropic covariance, or you could be a physicist. Because of course in physics, these functions are just spin glasses. That's all it is, right? So this make covariance structure the covariance of what is called a mixed spherical spin glass, right? So if you know anything about spin glasses, you know that they are not very simple functions, right? So let me come back, and then you will notice that you realize, maybe if you, for those of you who know what a spin glass is, otherwise you're learning what it is, this is what it is, right? This is the Hamiltonian of a spin glass. A spherical spin glass here because I'm on the sphere. So you just take this thing, sum of the coupling constant, as we would call them in physics, then are random, IID, Gaussian, And then you superpose different p's, and this gives you a spin glass. All right? So that's exactly, so here I started with, you know, the simplest possible function on the sphere, and the simplest possible random function on the sphere is essentially the spin glass, which is very not simple. Okay. Now, are spin glass complex functions? I just said yes. So in the pure p spin, so let's go now to some results. This function is exponentially complex when n diverges. So pure p spin means you have only one p. So you take a homogeneous polynomial of degree p. It has exponentially many local minima, exponentially many local maxima, exponentially many local, critical points of any index. Right? So again, if n is 10 to the 9, you have 10 to the 10 to the 9 local minima. So not a very simple function, even though it's a polynomial. The anneal complexity is roughly half the one of the worst case. I gave you this result by Kozastov saying that there is a terrible function whose complexity is log p minus 1. If it's random, it's half of it, but it's still positive. So which means if you take the worst possible function, the number of critical points is of the order p minus 1 to the n. Here, this one is of the order p minus 1 to the n over 2. Okay? So still very large. How do you know? So random matrix theory, as I mentioned, and Katzreis formula. If you don't know what that is, I will remind you very quickly. In fact, very quickly, here it is. So the Katzreis formula is a very old thing, which goes back to the 40s. If you have a random function and you want to compute the mean number of critical points of this function f, of index k with values in B, is given by this integral. Integral on the set of values, integral on the manifold of two terms. Okay? And what are those two terms? This term here is the important one. It's the expectation of the absolute value of the determinant of the Hessian as a function, indicator of the index being k. You can forget that for the moment if you want. Conditioned by the value and conditioned by the gradient equals 0. Okay? So that's the important thing. And this phi, the other term here, is the distribution of the vector f grad f. Okay? So here, remember, we are in a situation where f is Gaussian. So here I have to compute the distribution of the Hessian condition on the value and on the gradient. Conditioning in general is very complicated, but in the Gaussian case, you can always do it. It's linear algebra. Okay, so this can be done. But look at it. This equation 7 is the link with random matrix theory. As I said before, this Hessian here is a random matrix. Forget the index for the moment. So here what you have to understand is the conditioning by the Hessian. You take your random matrix of size n by n or n minus 1 by n minus 1 on the sphere, and you condition by the value and by the gradient, by the fact that the point is critical. This means the point is critical. Forget even the conditioning by the value if you want for the moment. The important structure here is you take the Hessian at a point which is conditioned to be critical. This gives you a random matrix model. Okay? And then what you have to compute is the expectation of the absolute value of the determinant of this random matrix. Okay? So that's the mathematical tool to do that. All right? So why would that be simple? So if you want to understand this formula in depth, you have two very nice books by Azaiz and Schwebor and by Adler and Taylor. So the Katzreis formula can do many things. Note that this
Can you explain why this is a reasonable formula?
it is just
Something you'd expect, or is it something magic?
it's nothing magic. It's a trivial formula.
It's a trivial formula.
It's absolute. It's a change of variable. If you do it in dimension 1, it's f of b minus f of a equals integral of f prime of t dt.
But why is the absolute value?
So that's because here, so that's a very good question. So let me come back to that. This is a very important question because the absolute value is a pain in the neck. It's extremely hard. That's what makes this whole thing difficult. But you also have formula without the absolute value, but then they are not related to the number of critical points, but to the Betti numbers, to the other side. So the other side can be computed without the absolute value. Here you need
Formula true if I remove expectation on both sides.
Then it's not true.
But then it's not a trivial formula.
That's what I'm saying. This is a Neal formula. You may have a way, so you may want, and we'll come back to that, to compute something quenched. Okay? All right, so that's what I'm saying here. It gives you only the annealed version. For instance, it gives you the expectation of the number of critical points, so the log of it, and not the quench thing, which is the expectation of the log. And these two quantities might differ, and they do differ in certain models. Right? So we have to be careful. I will tell you how you deal with that. Okay. There is a natural way to try to compute the quench complexity when it coincides with annealed complexity. And of course, it's to compute the second moment. You have a Katz-Rice formula for the second moment. If you can, which now you will have, it will be more complicated. You will have pairs of random matrices instead of one random matrices. Because if you have a second moment, you would have two points like that. And then you compute hard, and then if your second moment is such that it's very close to your first moment square, then it means that your variance may be small. If you can control the variance, then you can prove probably that something can concentrate on its mean. So you prove that the quench computation is equal to the annealed computation. All right? So when the quench complexity is the same as the annealed complexity, this approach can give you the result. So this was done in particular in the example I want to treat here by Eliran Subag from Weizmann for the spherical spin glass and used to understand in detail the structure of the Gibbs measure. Okay. When the two complexities are different, that's the question that was there, then we are at a loss. Not a loss function, we are lost. We don't know what to do. Except there is no serious mathematical proof. Remember that for the free energy of spin glasses, it took 700 pages of Talagrand to go from anneal to quench. So that's not a trivial matter. So if somebody is courageous enough, there's probably a way to adapt the Talagrand type of proofs, the cavity method, the Guerra cavity method, to do that. Okay? We didn't. We don't have the courage, but you're younger, maybe you have. So and by the way, let me just say a word. Guerra passed very recently, so let's have just a minute, a second of thought for him. But in fact, of course, physicists are never completely lost, of course. They all have tricks. So here the trick, there is, if you dare to use the replica method, the Parisi replica method, you know, simple things like integers between 0 and 1 or something like that, then it works. Then you have a formula. And this replicated Katz-Rice method was introduced in this paper. Giulio is here, Valentina and Chiara are not, but and of course, I was very happy to see this happening, but as a mathematician, it makes me a little... But the formula is right. Now, you know... Okay, so if somebody has an idea on how to compute this quench complexity when it's complicated, when it's not the same as annealed by rigorous mathematical methods, that would be great. Okay. So Katz-Rice here makes this link, and the Katz-Rice formula reduces this story about the understanding of this random matrix model. So why would this thing be this? Now I say this reduces to a random matrix problem. Why would this random matrix problem be simple? Right. So first, the function is Gaussian. So the Hessian is a Gaussian matrix. It's a Gaussian real symmetric matrix. This can be still extremely complicated. Right? But here it just happened that we have something, that we have, so you have this Gaussian matrix which defines a 4 tensor, right? When you have the matrix is a 2 tensor, so you have a 4 tensor for the covariance. And so you have to understand what this structure is. But here, there is something that simplifies the matter mostly, and I already gave you the argument. The important thing is that this random polynomial, these spin glasses, you could look at them as Gaussian processes with isotropic covariance. They are isotropic, which means if you do any rotation, the distribution of your polynomial will not change. So the Hessian should also be kind of isotropic, right? What kind of Gaussian matrices do you have which are isotropic? We understand them. They are necessarily not very far from the simplest of all random matrices, which is the GOE, the Gaussian orthogonal ensemble. And this is what happens here. These things are small variants of GOEs. And then for GOEs, we have a whole bunch of tools, including large deviation, and using the large deviation for this thing, which we proved with Alice Guillonnet 30 years ago, this can be done. Right? So here it's a nice model because you can go to the end of the computation because the Hessian is not too complicated. Okay, that's the link. That's just what I said. Oops. Simplest cases, here is some literature on these things. The simplest model is this, and then it becomes more complicated. So that's the link with random matrix theory, from which you get all this information. So this is the joint paper I mentioned with Yann Lequin. And this has been pushed to, but in general, in more complicated models, the random matrix model that is behind this is usually very hard to study. So again, if you have energy, look at one of them, understand the spectrum of these things. So some recent progress on random matrix and by Laszlo Erdős, his collaborator, and with Paul Bogat, Ben McKenna, and myself, have allowed to do more things. But let's much more needs to be done on this thing. Okay, so back to polynomial. That's our spherical spin glasses. That's the one I have defined before. Here it's normalized like a spin glass, and here I call the coupling constants like they are called in spin glass literature, J. Okay, this is what I was explaining before. I don't know why. I'm sorry, this is a repeat. Here is the theorem I wanted. So I told you that this complexity is complex, is exponential. So here's the theorem. If I look at crit k, the number of critical points of index k with values in E, with energy value less than E, NE, N is the, yeah, maybe I should draw a picture here. In this context, with the normalization I was given here, the energy levels are like this for this function. The typical energy level is 0 because my thing is centered. The typical fluctuation around this with the proper normalization here is of order root n. And the lowest point, the ground state, is at a value minus n times a constant. So the very low energy levels, the point we're trying to find, the minimum, is at minus n. That's just a matter of normalization. Okay? So what do we find here? We find that the anneal result, the log of the mean of the number of critical points of index k, here k is fixed, think k equals 0, so we are looking at the local minima, is a certain function theta k of E, depending on the value E. Okay? So this, if you read this, so it tells you that it's exponential because, in fact, what we find is that these functions have a shape like this. That's theta 0, right? And so that's theta 0 would be the complexity of minima. When k equals 0, we're looking at the local minima. And there is a value here where it goes from negative to positive, right? When it's negative, when theta 0 is negative, look at this. It means that your mean number of local minima is exponentially small, right? Because 1 over n log of that is negative. So it's exponential. So on this side, it means you don't have exponential, you don't have critical point, exponentially many critical points, right? So on this side, in fact, you don't have any, as we'll see. But here, the number is exponentially large, at least the annealed number. And then you have the same thing for E1. So now if you look at the number of critical points of index 1, so saddle points of index 1, it's also exponentially large by the same result, but above another threshold. That's theta 1. And then you have the same thing with theta 2. So same thing, you have different heights at which, so here if I draw it on this picture, you have here a level minus n, negative n E1, above which you have saddle points, of index 1, but below which you don't. But in this interval, you have exponentially many local minima, but no critical points of index larger than 1. So which means that here you have wells, right? And you have to climb above this to join them, right? And then you have the same thing with all the others until a level which is minus n e infinity, right? And what you see here is that above this level, which is very low, you don't have any exponential. That's the place where all the critical points of finite index are. Above this, between here and there, you have plenty of critical points, but of diverging index, which means here, when you're below this, you have critical points which have a finite numbers of way to go down. That's what the index is, right? They have a finite number of negative eigenvalue for the Hessian, right? So you have, if you are this near this such a critical point, you have, let's say, 10 to the 9 minus 17 direction, which are going up, and 17 direction going down, right? So it's hard to go down, right? Whereas when you take critical points around here, let's say around 0, it has half directions going down and half directions going up, which seems natural. Okay. So that's what. So that's these are the annealed estimate, and as I said, Subag proved using the second moment and the Katz-Rice method the quench estimate when you take this expectation and you put it there, right? Which then tells you all you need to know. He proved it essentially for energies E which are very close to this ground state initially. Okay, so this function is very complex. That's what you have to think. And so you have plenty of critical points, and in fact the picture, so now you could think, if I take a local, I have plenty of local minima, I have exponentially many of them. When I want to move, so first, now, let's imagine I'm doing dynamics here. I start from a point at random, I want to find the absolute minimum. If I start at random, I start around here, right? A point at random, the energy is typically 0, that's the mean. And then the question is, how much time does it take to come down there? Right? And will I get stuck into wells above that, et cetera, et cetera? And of course the answer is, yes, you will get stuck. The time to go down is exponentially long. The system shows aging, like a glass does. You can compute many, many more things. It's a terrible, terrible dynamics, right? So if your goal in life is to find the minimum of polynomials, you can't, right? In high dimension, you just can't. Except if you're ready to wait for ever.
Is there a stronger analogy to quanta here? Like these different E1s and E2s can fall up from some wave equation?
You could, but I don't want to go there.
Okay.
No. Yeah. Okay, so here's an idea of the proof. If you use Katz-Rice, the expected number of critical points of index k whatever is given by, say, this big formula with an absolute value of a determinant. You work like a dog on it, and what you find is this expectation under the GOE, as I mentioned before, of exponential minus a constant times the kth eigenvalue conditioned by the value of it. Right? And so now what you need to understand is how do you estimate this type of thing, and you need large deviation estimate for the kth eigenvalue, which just exists in the literature. Okay. For general, I'll just skip. Yeah, so this, as I said, this was done almost 30 years ago, so it's easy. Oops. All right, so if you want, there are, I give you more references. Here they are, Aufinger. So the paper I was mentioning giving these results is by Aufinger, myself, and Tuka Aufinger and Jiří Černý. And this is the paper we discussed with Yann Lequin a long time ago, right? This is this thing. What does it have to do with machine learning? So once you have this, if you now, let's say, imagine that This is a natural topic here. Let's do a little bit of physics. Once you've understood the temperature zero picture, what do you understand on the Gibbs measure? So you do understand a lot. So for instance, see Subag or Subag, Zeytouni, and myself, and also all that. Let me explain what happens. I will explain on this thing here. What you have here, so now think of the Gibbs measure at low temperature. So as I said here, there's something we have to understand. You have exponentially many local minima in this regime, certain much with a higher thing, certain very deep. The Gibbs measure will be concentrated at low temperature on rings in those. If you fix the energy, it's the same as fixing the temperature. The Gibbs measure will be concentrated in rings on those things. Another way to look at it, of course, it doesn't make sense. Imagine this is the sphere in high dimension. You have this bottom of the wells, and you will have rings around them. The Gibbs measure will be like that. Of course, such a ring is itself something like a sphere in dimension n-2. So it's still a very high dimensional object, right? But you should look at them like this. You have wells. Clearly, when you fix the energy, it's the same as fixing the temperature. So you should have rings. You take a well and you just fix the energy. This gives you a ring, and the Gibbs measure should be concentrated there. The real question is, which rings? Because you have exponentially many of them. So is the Gibbs measure carried by infinitely many of them? Of course, at low temperature, it's not supposed to be like that. So only a few are selected. Right? You have exponentially many local minima, including very deep. Only a few are elected to be the carrying the Gibbs measure. Right? Why? And so, in fact, the ones that are chosen in the pure p-spin model are the deepest one. So you take the deepest one, the second deepest one, the third deepest one. It gives you a sequence of wells. You put your rings in them, and the mass, which means the mass of each ring, form what is called a Poisson-Dirichlet process, well known in extreme value theory in statistics. And you will see that coming again when Giulio speaks about the random energy model at the end of this. Okay, so the Gibbs measure is perfectly understood at low temperature. So the local minima which carry those rings are the deepest one. But not in the mixed model. In the mixed model, you have something more complicated, which is called the temperature chaos, which I will skip, where these wells which carry the Gibbs measure change with the temperature. Whereas here, they don't change. If you take at two different temperatures, your Gibbs measure will be carried by wells which will be here. So at this temperature, they will be carried by these rings. At a higher temperature, they will be carried by those rings in the same wells. Right? Remember that you have exponentially many other wells, and they play no role for the Gibbs measure. Right? Which tells you that the Gibbs measure, the statistical physics approach, doesn't give you enough information on the landscape. The topology information is much better. Starting from temperature zero is much better than starting from just looking at the Gibbs measure. Okay? Now, so in fact, this story is valid up to a temperature corresponding to this level, which is called the dynamical transition. It's valid, I'm sorry, to another temperature, which is here, which is called this, I would call, let's say, the static transition. So up to a certain energy level or temperature, this picture is valid. Your Gibbs measure is, sits inside all those wells. Above it, it's not like that. And so, for instance, what you can prove is, okay, with Aukosh Jagganath, we proved something. So here's the picture. I will just tell you what's going on. Above this thing, if you take 2 points at random under the Gibbs measure, two replica à la Parisi, and you look at their overlap, it will be 0. Why is that? Because, okay, what is the structure of the Gibbs measure here? What is the overlap? If you take, in this context, at low temperature, if you take 2 points independently under the Gibbs measure, two things can happen. They can be both in the same ring, or they can be in two different rings. Right? If they are both in the same ring, they are randomly chosen on the sphere one dimension less, so their overlap will be a function of the radius of the sphere, will be a certain positive number. If they are in two different rings, these centers of these things are orthogonal because they are points chosen randomly on the sphere. When you choose 2 points randomly on the sphere in high dimension, they are always orthogonal. So these 2 points will be essentially orthogonal, so the overlap can be either 0 or a positive number. You have two possibilities for the overlap value, which is what is called one replica symmetry breaking. Okay? So this one replica symmetry breaking is happening here, but normally you have another temperature above which, so this happens until TS, the static transition. And then above that, when you take 2 points at random, their overlap is 0. Right? It's under the Gibbs measure. It's as if you had chosen them completely uniformly at random. Even though this is true, there is a hidden phase here, which for statistics will be horrible. There is what is called a shattering phase. When you are above, between this temperature and that temperature, the Gibbs measure is in fact made of rings like this, but exponentially many of them. So your Gibbs measure is completely shattered. So this structure is very complicated, not at all like uniform measure, but still, when you take the Parisi parameter, it doesn't see it. Because if now I take 2 points at random in this thing, they will, with very high probability, be in two different things. So their overlap will be 0. So the Parisi parameter, the overlap of two replica, doesn't make a difference between the shattered phase and the very high temperature phase. Now think a minute about optimization. Imagine you want to find the minimum of this thing. This is much more terrible than a uniform measure. Because if you come down and then at some point you can be hit or you can be stuck by one of those exponentially many traps. Right? So this is a bad thing. So what we prove there is that this shattering phase does exist, and and not very good news. Okay. I will not give you this brief history. This is too long, nor even the result, maybe. Now.
Could you say again?
Yes.
For temperatures below TS, the Gibbs measure is carried over a finite number?
A finite but diverging number, right? That's the Poisson-Dirichlet. So in the end, your measure is carried. You take the deepest well, the deepest minimum, the second deepest, the third deepest. You look at the rings around each of them, and these converge when n is large to a Poisson-Dirichlet process, and this is the Gibbs measure, right? And this is exactly what happens in the random energy model, the simplest of all spin glasses. Okay? Now, here is a few conjectures. All right, so forget the first two. That's a little too technical. Let's get to conjecture 3. So here, what I was describing is some geometric, it's a long work, but I'm just giving you the picture, a geometric picture of this crazy polynomial, right, at low level. At very low level, the Gibbs measure is carried by these few things, like a heavy tail type thing, and then you have this very many, and which, that's the picture. But now we could also look at the dynamics. Okay, so let's think a minute about dynamics. Here I'm on the sphere, I have this function. So what are the natural dynamics? I could do stochastic gradient descent, but it would make no sense here. We're in physics. So if this is a problem of physics, you do Langevin dynamics. All right? So you take Langevin dynamics, you all know what that is. That is, you take essentially a Brownian motion in this potential on the sphere. And you want to understand how much time you know that this thing is reversible. So you know that, and you know that the Gibbs measure is invariant. So you know that at some point this thing will converge to equilibrium. How much time? So what does happen here? So let me erase all these things. Now if I do the picture for dynamics. For dynamics I have, so that's again now, let me put the temperature rather than the energy. I have temperature 0, I have infinite temperature. Okay. So how can I quantify the fact that the convergence to equilibrium is fast? How would you do that? If I give you a stochastic process, a Markov chain, here a Markov process, what is the natural way to say that it converges fast? Yeah, the spectral gap, the mixing time, if you want, something like that. Okay, so you look how much time it takes to mix, right? You look at the spectral gap. So the mixing time, so the question is, you imagine that at high temperature, the mixing time should be finite, right? And at low temperature, it may be very large. So that's exactly what happens. At low temperature, the mixing time is exponentially long. It takes exponentially many steps, much time to get to equilibrium. At high temperature, it's finite. But there is a transition between the two, right? And the physicists give us this transition at a temperature which is called TD, dynamical. So the question is this thing the same as the place where the shattering phase appears? Who knows, right? So that's an interesting question. But first, this is not the place where the mixing time becomes short. Right? So what physics does, if you read this literature, is very different than what computer science does, algorithms and math. Math would look at mixing time and spectral gaps. Mixing time means, it's again for pessimistic people. Physicists are optimistic. Right? So mixing time means your thing will converge wherever you start. Right? Uniformly in where you start. Right? So, in particular, this means it's adversarial. If you let the devil choose the bad point, you still can be sure that it will converge. Right? Physicists don't believe in the devil, obviously, because the way they define the dynamical transition is with this thing, which is the thermalization time, which is not the same as the mixing time. Thermalization means you start at random. So you don't let the devil choose the wrong place to start. You start with a typical point, typical configuration, and you look at how much time it takes to converge. So it's much easier to thermalize than to mix. Okay? So the temperature for the mixing time is supposed to happen at a higher level. And it does, in fact. So above this temperature, the mixing time will be short. Below, it will be long. Above this temperature, the thermalization time will be short. Below, it will be long. Okay? So when you are in between here, it means that if you start randomly, you will converge fast to equilibrium. But if somebody is perverted enough to make you start from the wrong place, it could take exponentially long. Okay? So that's the story. I'm summarizing something like 300 pages here, so I'm fast. So here's a question. So this BBM, it's this thing. So BBM is not BBP, it's Barra, Burioni, and Mézard. Okay, so we make this conjecture. Is it true that the spectral gap is bounded below when you are above it? So what I was saying is just a conjecture. We are not completely sure, but it should be true that above that, everything is cool. Right? The spectral gap is bounded below, so convergence is simple. The thermalization time, in fact, should be fast above a level which I call here TS, SH, and this too should be the same. TSH is for T shattering, right? That's the place where you have the shattering, and so these two things should be the same. And thermalization should be fast above that and slow below that. Okay, that's the two conjectures. Some of it is proved. Okay, I won't spend time with that.
But from a topology, there is something topological that happens between TD and TBBM? Or?
I'm sorry, there is?
So, if I understand well, below TD you have a lot of minima, no?
Yeah.
And the
No, you have always a lot of minima. Below this, you have plenty of them. The important thing is the structure of the Gibbs measure. You have another one here, which is T static. That's where the Gibbs measure is. That's where you have the Parisi transition. Below that, you have this. The Gibbs measure is concentrated in this Poisson-Dirichlet type structure. Here, the Gibbs measure is shattered, right? You have exponentially many things, right? And above that, if you start at random, your dynamics should be fast. Below that, the dynamics is slow and ages. No, okay, now I would explain. Okay, I understand your question. I'm sorry, I didn't get it. No, the minima stop, I'm sorry, the minima stop here. But minima have wells. So you may have a well here, you may have a minimum here with a well that goes much higher. And so now, if you could start, why do you have some bad, when I say the devil chooses where you start? If you start from this thing, then you will take a very long time, even if you start at a high altitude, right? And so that's, but the Gibbs measure of this thing is, the measure of this thing is tiny. These are tiny, tiny places. So if you start at random, you will never start from there. But if you let somebody force you to start there as a theoretical computer scientist, then you go down there, and what happened is that above, the conjecture is that above this thing, all these wells have evaporated, right? They kind of disappear. And here you don't have any such things. You still have exponentially many critical points, but of diverging index. So if you have a critical point of index n over 3, it means that you have n over 3 direction to depart, so it's not too long. You don't wait too long, right? That's the idea. Thierry, c'est la fin là, non? 3 minutes.
2-3 minutes. It's just a question by law.
Is there a notion of well-prepared initialization for, or is it just something which is, say, almost sure, or you can define a way to choose your initialization?
No, here, so that's what I'm saying. Yeah. So here I'm saying, above this, if you choose at random.
Yeah, at random. But you don't have a criterion to choose it.
In fact, yes, there is one, but it's. So you have. So here, let's say the pessimistic side is easy to say. I can find a place where if I start, it will be slow. So I tell you even geometrically what those places are. Now you're asking a harder question, which is, if I'm above this, for what kind of initialization will I work? It's in fact clear. It's those who, it's not written, but I'm giving you my impression. It's of course those initializations that don't give positive mass to these bad places. Right? If you are in a place which brings you to one of those wells, then you will take forever. That's,
but you don't know in advance.
You don't know in advance, of course, no. All right. So this explains, okay, I will just stop here because this goes to, this is the story I told you, but with formula.
Well, thank you very much. Are there any questions? Oh, sorry, yes.
I'm just wondering, am I right to think that this T static is the same as minus, is the temperature associated with minus E0, or is that?
No. Minus E0 is associated with 0 temperature. This is really a different temperature. And it's below this, so it's in a region where you have critical points of finite index, plenty of them. It's a place where this Poisson-Dirichlet structure, whatever, stops to exist. And so in physics terms, it's where you go from one replica symmetry breaking here, replica symmetric above.
But so this graph you showed where it says that there's above minus E0, there's exponentially many.
Yes, in this region you have exponentially many critical points of all sorts of finite index. And what I was explaining is that the Gibbs measure chooses only a few of them to be carrying the Gibbs measure, for whatever reason. Okay. So of course this is physics, and that's the end of physics for these lectures. The next time we'll do statistics and machine learning. And the first example will be, as I said, Tensor PCA, which is a problem of estimation of tensors. But when you look at it, it's the spin glass that we just discussed plus a signal. Why is it the dynamics is so slow here? Is because you have no signal, of course. Now imagine that you have a signal. You want to force your thing to go somewhere. Then things could be a little different, right? So, and this is a statistics problem that we'll treat next time as a first thing, and then we'll go to a more general situation of machine learning type things.
Yes. Are there any more questions? Just very quickly to summarize, so this is a generic behavior for p-spin phi larger than 3, and but for SK you don't have this intermediate space. Is that right?
For SK it's different because for SK you have a full replica symmetry breaking. So for instance, there's another. If you really want to have the full thing, is you look not at SK, you look at the p-spin, but on the cube. Right, Ising's p-spin, right? Then you have much more complicated story. You have 0, you have a first transition, so where you have here full RSB. Then you have so this is Gardner transition. Then you have one RSB, which is this phase here. And then you have replica symmetric, in which you have also a shattering phase, like here. So in this picture, you don't have this. In the p-spin on the sphere. For SK, you don't have this. You have directly a transition from here to there. But for general p-spin, 3 spin on Ising, you have the 3 phases. And this transition is super interesting. That's the real glassy transition. But this one we cannot attack by topological complexity easily, because this is a discrete model. So I cannot compute the number of critical points or whatever. So the only way to do that seriously is to use the tap complexity. And this is why I mentioned that. But the tap complexity is now understood, not published because we are slow, but understood at the level of annealed, but you have to understand it quenched. And for quenched, as I said, so that's why I was asking the question, the only way we have to compute mathematically, seriously, the quench complexity is when it's 1 RSB, when anneal equals quench. But in this phase, I have no clue how to compute, except if you use the beautiful paper by Giulio that I mentioned, where we use the replica trick, by Giulio, Valentina, and Chiara, okay, and myself. But you understand that on this part of the computation,
But in any case, by the end of the 2 weeks, it's an interdisciplinary conference, so by the end of the 2 weeks, all the mathematicians will also use the replica trick.
Of course, of course.
Thanks a lot, and we'll see you tomorrow.